In this lecture, we will cover RGB visual odometry. We're going to see how we can use a type of camera from the category of depth camera that gives you RGB measurements in form of images and depth images in form of another image that tells you what's the depth, the distance of each pixel from the camera lens. And then together, we can basically construct a point cloud that has color information. We want to see how we can use this camera to reconstruct a scene. And to do that, basically we need to track the camera poses over time. So that's the context of visual odometry. It can be done with monocular camera or stereo camera or RGB camera. I'm going to use an example from TUM dataset for RGB SLAM. I made well, first of all, this is a room. You see this teddy bear. There are a lot of sequences, but this particular sequence, it goes around the teddy bear. We want to reconstruct the bear. And as you can see, the image is blurred, and that's a problem because this particular camera has a rolling shutter. As the camera is moving, the shutter is also moving to capture the scene. And that causes motion blur, which is best, as far as we know, it's understood as convolution along a time channel. So that causes motion blur, and consequently that will cause difficulty for registering this image with the next one to find out what's the camera pose. We do have cameras with global shutter, and obviously that's preferred because they capture the entire image at one instance. And that you don't see motion blur as much as you see here. And this is an example of the depth image. The depth image, you do need a scale to know the actual metric value. But based on the image, you can tell that, where is Teddy's arm? Can you tell that? So this is Teddy. It's closer to the camera. So the darker value is closer to the camera. The brighter pixels are farther. Is this perfect? Can you see? It's hard to see in class, I think, because of the light. But this is far from perfect because some of the pixels are missing. The boundaries, the edges of some shapes, for example, you can see this is a laptop here, but the shape is not exactly like what we see in the image, and that's a problem. That means not all pixels come with accurate depth, or sometimes we're dealing with missing depth values. Okay. So this is the video, it's a GIF image that playing all the images recorded by the camera. This is how the camera is moving in the room. This is the 6 degrees of freedom movement. The camera can roll, can pitch, can yaw. There's the X, Y, Z movement. We see we can zoom in, zoom out. And all of these motions can be done at the same time. So the faster you move, more motion blur you see, and it becomes harder to register. The more overlap you have between consecutive images, that makes the problem easier because we're solving for the smaller motion. As you move faster, that makes it more challenging. And sometimes becomes impossible to track, which we might rely on complementary sensors for estimating the camera motion while we're registering images. For example, modern cameras come with IMU. You can use IMU to fuse that with image information to get visual inertial odometry. Now, another point that you might notice is that although there is someone standing there, the environment is static. If the objects are moving and the camera is also moving, that will make the problem even harder because we do not have any knowledge of object movements and we do not know the knowledge of camera movement. We need one of them to be our reference to estimate the other one. If both are unknown, that makes it very challenging. So we can track objects in the camera frame as it moves, but that will be relative. One idea is that if you can detect the dynamic part of the image and remove it, then maybe you can work with the static part to solve the problem. That's somewhat an obvious idea. Discard dynamic information. The more challenging will be how can you actually use the dynamics of the scene to make your tracking better, but that's a much harder problem to solve. Now, the depth video that you see here is for the same images. However, the camera that we buy has two different sensors for getting the RGB data and depth data. And these two sensors are not necessarily perfectly co-located. So these two sensors are somewhere on the camera, and these images are not perfectly rectified. They're not in the same frame. We will not dive into how to do this low-level signal processing. Luckily, when you buy this sort of cameras, usually they come with drivers. The driver usually developed with by the manufacturer, by people such as yourself. They just sit down and build a driver and make it open source usually so we can use it. It could be a ROS package, LCM package, or some other software that you can run on your OS. Then what we get registered depth and image data. First of all, they're synchronized. They might not be synchronized necessarily. Imagine the frequency of RGB sensor is different from depth sensors. Once we register them, then we can get synced depth and RGB images, and potentially with some intrinsic calibration that comes from factory, you can get point clouds. Okay? And if necessary, we might need to recalibrate the camera, intrinsic parameters of the camera. Okay, but when you want to deal with a problem for the first time, you can use one of the data sets. They usually come with calibration parameters and all the pre-processing using some tools that are provided. So that's a good way to focus on the algorithmic side of it, and later you can look into those parts if you're interested. With that, let's start. See how we can together formulate a problem. The way I want to formulate the problem is using nonlinear least squares. Nonlinear because we will see it ends up being nonlinear. And we'll try to come up with ideas and see how we can formulate a least squares problem that finds this camera pose by aligning two consecutive images. So in some sense, frame-to-frame RGBD registration, it's similar to point cloud registration. Because we could work with point clouds directly, and we could, in fact, use previous methods that I discussed that we can integrate color and point cloud. The RGB registration idea came after this. What we talk about is something that was published before that. But also the objective function that we derive today is important because something that is called photometric loss function. When next time we talk about the SLAM, when I show you an edge in the graph, we say, for example, this is a photometric factor, then you know what to think about. This lecture is a building block, is an edge in maybe a graph that we use for formulating a SLAM problem. So let's start with the problem of I think this is lecture 18, and we will talk about frame to frame, for short, RGB deregistration. Or you could think about of this idea as RGBD, visual odometry. Now, the visual odometry does not need to be just one frame to another frame. We could work with a sequence of frames, and that's usually how it's done. That's called a sliding window optimization. Or we could just maintain the entire history similar to SLAM. But when it's odometry, that means that there is no global loop closure. There's no history tracking that globally we go after a long time, we come back to a place and know that's the same place, and we try to remove drift. When we have that, that's SLAM, simultaneous localization and mapping. If you're working with a sliding window and rely on local constraints to improve your estimate over window of time, that's usually called odometry. So frame-to-frame registration is the building block. It's the simplest way of solving that odometry problem. So it's necessary to learn it, then you can build on it by solving many of these frame-to-frame at the same time over a window of time. And the window slides over time, right? You add new frames, you ignore old frames. That's the idea. So we to show you some examples of this camera. So a lot of you probably have seen Microsoft Kinect. Maybe you played with Xbox. That was the first one we were using for RGBD SLAM. It wasn't built for robotics, but smart people could make a driver for Linux, then we could run it on Linux, and that's how RGBD perception research started. So that's the importance of having the hardware, actually having the sensor, the hardware, so we can collect data and then solve problems causes huge progress, because suddenly now people can bring in a lot of ideas that we might know to reality. So it was enabled by having sensors, and maybe the most recent one, I think it was discontinued, unfortunately, but we should see different companies making different versions of this. This was an RGBD camera by Intel that comes with an IMU inside. And you see it on a lot of robots these days. They use this camera because it's small, it's relatively cheap, and works well. Although it's good for indoor, if you use it for outdoor, you can solve the problem for short range, 5 to 10 meters, but the point cloud will become noisy, as we will see the brightness constancy assumption will be violated. We'll talk about it. Okay, this Okay. This page is filled with motivation now. Somebody was asking motivate more before talking about math. I'm dedicating one page to motivation. I hope this satisfies you. So the camera, our algorithms are somewhat agnostic of what brand of sensor you will buy. We're going to assume the data is processed. We have synced RGB and depth images, plus we know the calibration, intrinsic calibration of the camera so that we can project 3D points on the image using the projection model of the camera. Because if it's not calibrated, that projection will be inaccurate. Then the model won't capture what we see in reality as good as we hope. So the camera gives RGB and depth images. Where to start? Where do you think we should start for formulating a problem? Day one, you started your job. Your supervisor gives you a camera and asks you to see if what you can do with this. We want to see if this line of work is promising for the robot. And you know nonlinear least squares from this course. What would you do? I don't want to write it for you all the way. We want to make it a case study based on what we learned.
So you're trying to define the models?
We need a model. We need a constraint. We need some sort of constraints that relate this pose that we are interested to estimate shows up somewhere that we can minimize some sort of distance, some sort of residual cost, right? That's the key. Once we have that, we can just go ahead and define the least squares problem by sum of maybe squared versions of that residual. So we need a model, then we need to define a residual for the optimization, a cost function. So a good place to start is lay out what we have. What's the goal? Tracking the camera pose temporally. So the goal is, or objective is, track the camera pose temporally. By temporally, I mean we are dealing with sequential images. And we're going to focus on the simplest case, because if you can't solve that, there's really no point making it more involved. So we're going to collect some data from camera, and maybe if I add the images, we can see what we can do. Keeping them roughly the same size. All right, so what we have, we're going to focus on T1 and T2. At time step 1, I have one image, and it's understood that it has depth image as well. We know we have that. And at time step 2, I have another image. You could call this image number 1, and maybe this is image number 2. Now, what I want to know is how the camera moved in 3D so that it observed the second image at time step t2. Now, that parameter we have from our previous knowledge, we know that this 6 degrees of freedom motion that can have rotation and translation is necessarily on a Lie group, and that's SE3. So we immediately recognize that the parameter that we want to estimate is not just a typical vector, it's a matrix. It's an element of a matrix Lie group. And we're talking about a camera maybe, right? It's moving from time step t to time step t1 to t2. Now, from the documentation of the sensor, I'm going to assume you read those, just like you read the entire 100 pages of IMU documents that I gave you in homework 4. I talked with a couple of students, and they know every word of that document. So I trust you read this one too. So we have a camera projection model. Well, this particular Intel camera, you can find it on GitHub. There's a repository that's also compatible with ROS. So if you buy the camera, you can just run the ROS package and you can just stream data in RViz. It's pretty straightforward to see the data, but the rest of it is our job. Camera projection model is provided. So suppose there is a, now this is something that you might have learned in your undergrad computer vision course. If you took a computer vision course in grad school, they might have covered this. It's a geometric model that when you see a point in 3D, it tells you a model that will project it onto the image plane. If you have not seen it before, that's not a problem. You can imagine this is a given model for this sensor. So the model tells us that if I have a point such as P, X, Y, Z, this is a point in 3D space, I can project this point to pixels. U and V are pixels. So my projection function pi will take this point, and U and V will be like this. The focal point of the camera, focal distance of the camera along X times the value of the coordinate of the point along X direction divided by Z plus some distance from the center of the image. And I'll tell you why. We need Cx and Cy. Now, the focal length of the camera along y-axis, it might be different. Pixels need not be squares. Maybe pixels are rectangles. That's just a piece of information you need from manufacturers. But when you calibrate camera, typically you can solve for different values of fx and fy. So f y times y divided by z plus c y. Now you can write this in a decoupled way. There's a calibration matrix, usually named k, and then you have your 3D point divided by z. So this is this, and you've seen this, I believe you've seen this in homework 3. When There you had two cameras, there was an object, you want to estimate the position of the object. So this was the model. Is this model linear or nonlinear? Nonlinear. Why is it nonlinear? Because we have division by z. That makes it nonlinear. So this is 2 by 1, this is a 2 by 1 vector. To make it clear, it is common to use coordinate frame like this in computer vision when you have one axis along the height, started from the top of the image, top left corner. The positive directions are pointing down and to the right. Typically, this is U, and this is V. If this is center of the image, then we will need this C values to reference it with respect to the origin that we chose to be the corner of the image, not the center of the image. So these Cx and Cy are for that. So we have the model. What's next? Looking for ideas. While you're thinking, I'm going to make another simplification. So RGB image has 3 channels, red, green, blue. We could try to use each color as a separate measurement, or before deep learning, in this context, as what you see in literature, typically the image is converted to grayscale. Then that combines all 3 channels into one channel, and then we work with intensity values. So that makes the problem a little simpler. But when you use deep learning, you can just give all 3 channels as the input. There's no need for combining them. So following what we read in the literature, images are converted to grayscale images. Now, the simplest way to convert a color image to RGB is just sum them up and divide them by 3. But better models exist, and they use different weighting for RGB, right? But if you use OpenCV or any other software or library, probably you have access to a function to do it for you. All right, so now we have intensity. I'm using I again for intensity, but also it stands for the image. From image 1 to image 2. What's the constraint here? I need to define my constraint so that I can measure error. If you cannot measure error, you cannot minimize it. If you cannot minimize error, there's no objective function to estimate the variable that you're interested in. So we can work with something that we can measure.
Could a constraint be that any corresponding key points on or at the objects in the scene are static? So any sort of transformation that we have is the camera's transformation. So if we're tracking a single point on the image, then we can track the error that is projected from one to another. Like the difference can then be whatever the projection on the image plane can then be translated to the motion of the camera itself.
That makes sense. So you're saying that, well, first of all, we should think about these intensity values as measurements. We just have a lot of measurements. That's why perceptual sensors like LiDAR or camera are high bandwidth. The amount of data we get is extremely higher than something like IMU, which is just a signal, 1D signal for each dimension against time. So for example, this can be 320 by 240 image. Which is a reasonable size to work with, but that's pretty small. We can get probably HD images from the camera. But that will be probably too many pixels to work with. It takes longer to process them. So that's already more than 600,000 pixels. That's a lot of measurements for one time step. So the constraint that you pointed out, Honor pointed out, is that if the camera moves, the environment is static. Can I assume that what I see should be similar to what I observed before? There's just change in the viewpoint, and if this pose can capture that, I should see the same pixels again. And exactly that's what we're going to assume. And the assumption is called brightness constancy. So it's important when you model, you list your assumptions. If your assumptions are not clear, that leaves others to wonder, what's the scope of your model? When it's valid, when it's not valid? The model is not valid when assumptions are violated. And that's how you can explain when something doesn't work well in practice, you go back and look at your assumptions. Hopefully your assumptions are reasonable and reflect your model. Then you see if they are violated. If they're violated, you can explain, probably that's why your performance is not very good. So the assumption is called and the brightness constancy is saying that if you move a little bit, not a lot, under small movements, the intensity values of the corresponding pixels are the same. So that gives us a way to re-observe this one pixel again in the next frame. Therefore, now we can talk about the difference. If I minimize the difference between pixels that are re-observed, the pose that describes that minimization the best, that's my solution. So that's the idea. Now, this assumption is easily violated, right? Is there a typo? No? You should be kind and tell me if there is. English is not my first language. Okay, so if the camera moves, a lot, this assumption is easily violated. What's another case that the assumption is violated? There's a very obvious case that you should be very careful when you use this method and look whether that environmental condition exists or not. variation in lighting, illumination change, that's right. So that's why it's so hard to use a method like this outdoors. Maybe it's a sunny day, the way you move, you might see glare in the image, and that can destroy everything. When it's cloudy and uniform, the sky light is uniform, then SLAM methods shine. When the sky shines, the SLAM methods are under the weather. So when you see a data set, it's a cloudy day, you know, they knew. You get best paper award. It even works outdoor. So it's not, that's a little sad because it might work sometimes, it might not if it's violated. We like to have methods for robot perception that they work under general condition that can change. So that's an existential limitation we have in robot perception. And we're trying to make algorithms better to work in different situations such as that. Okay, so assuming this is true, by the way, how can I read the pixel value when I know a pixel coordinates? Imagine I have this pixel here. What is its intensity? So I have my 3D point. There is a 3D point. And I use the camera projection model that will give me a pixel. I'm going to call this maybe point I, UI, VI. I'm asking you what is intensity of, or maybe you call it like this, UI, VI. It is a scalar, yes. It's certainly, it's just a real number. And it's a positive number because color values are positive. So it's a positive real number. Or sometimes people show it like this. How can I access this intensity value?
It's just a grayscale value, right? So you just index into your kind of like image that you saved.
Yeah. How can I implement it?
Like such that the center is in the same frame as UV?
Yeah, I have this in memory. It's saved in whatever way you want.
I guess I'm not understanding very properly.
So trivial that you're not even considering it. So you read it from the memory, right? So that's what you do. So there is no function, there's no relationship. It's stored in your memory, and you read it off the memory based on the index value. And that's OK for this method. In the previous lecture, RKHS, it's exactly addressing this problem that there is no model that is describing these relationship between these intensity values and the point in 3D. And that kernel density estimation that you saw is the weighted sum of labels. It is defining a function. It's a model. It's an analytical model that is describing the relationship between this P in 3D and these intensity or color values. So in this context, that model does not exist. That's something that you can go back and now compare these two. In this case, we just read it from the memory. That's fine. That's what we do. which, by the way, we're limited by the resolution of the image and data. It is not continuous, it is discrete, although we have a lot of pixels, and it works well in practice. So I'm going to need to define the residual now. So if I observe the point in, remember, we have the depth value. We have the points in 3D for the RGBD camera. If I observe the point in let me write it first. So I'm seeing a point in image 1 in 3D. And of course, I can read, for every point, you can read the pixel value. Because for RGBD cameras, there's a one-to-one correspondences. We have one-to-one correspondences between points in 3D and pixel in images. So whether you know UMV or P in 3D, you can read the intensity value from your memory. So I see the point in image 1, then I see the point again in image 2. The relationship that relates these 2 points is that if I transform the point in image 2 using this rigid body transformation, and then if I project it onto the image 2, I should get an intensity that is similar to what I had in image 1. I think, strictly speaking, we should write right? But again, this part is constant because it doesn't depend on the transformation. You just know it. It's a value. It's a scalar value. So see the point in frame 2, transform it. See the point in frame 1, transform it to frame 2, project it onto the image 2, read the pixel value, intensity value in image 2. Subtract it from the corresponding intensity value of the point we transformed in image 1. That's the residual. Could we do it the other way? See the point in frame 2, transform it to frame 1, and project it to onto image 1? Yes, we could. There's really no difference. You need to choose one. At least in frame to frame, there's really no difference. You're estimating T or T inverse. In any case, it's a rigid body transformation, and the optimizer does not care which one you're trying to solve for. Maybe if you're doing a sliding window or a slam, maybe you care about the order. But anyway, it will be similar to this case. So the action of rigid body transformation on a 3D point, because I'm not making the points to be in homogeneous coordinates. I'm not appending 1 to x, y, z. So I'm using this dot value to define action of T on P, which is rotate and then translate. And my parameter, the decision variable of the optimization, is an element of SE3. So how many of these residuals I have? $60,000? Let's say this is the image size. You're probably better than me in arithmetic. Multiply them and see what you get. More than 600,000, right? So the vector of residual is super long. It's unbelievably long if you want to use all images. If it's HD image, what is it, 1080 times 700 something? New TVs are 8K. So there's an idea in computer vision called image pyramid. So historically, when they have high resolution images, this problem is not convex for several reasons. First of all, the rigid body transformation has a constraint because R transpose R must be identity. That makes the problem constrained. Now, when we do it on Liguru, we do a trick using that exponential map to integrate. We ignore the constraint. But that gives us a local solution. The intensity values, if you visualize, right, this landscape of the residual objective function, it's not convex. It's not going to be a nice quadratic function that you find the minimum. No, there will be many local minimum. And the bigger is the image, the resolution, when it's higher, you get more of these local minimums, which makes it even harder. Sometimes high resolution makes the problem harder to solve. So the idea of image pyramid is that start from a very coarse resolution. When the image is coarse, the resolution is very low, you roughly know where you want to go because all those tiny minima will disappear. You're going to focus on the deepest minima available in the image, in the cost function. So do the registration in a coarse level, which of course you need to decide how many levels you want to perform. Use that solution to initialize the next step. Now you're around the minimum that is hopefully better than a lot of bad local minima that you see in the high resolution image. Then solve it again, move to the next step, next step. So you repeat this, solving the same problem maybe 10 times, 5 times, using this idea of image pyramid. So same problem, just change the image resolution. So obviously, it will make it slower. If you have to solve it 10 times instead of 1 time, that's a factor to consider. But it will improve your performance substantially because it will guide the coarse version roughly, it will do coarse registration, will guide the problem to a deeper minimum. The high resolution part will try to minimize the error around that deep minimum. So that's a very established idea, and you find it in computer vision textbooks as well. Again, linking it to the previous lecture, RGB registration, there is no need to solve the problem multiple times. Because of the continuity, the kernel bandwidth, that length scale of the Gaussian kernel that you saw, when you change that kernel, you remember that picture that when L was large on torus, we had a convex problem. As we decreased L, we got a lot of local minimum, right? So the idea of image pyramid relates to that bandwidth in the sense that using the bandwidth, you can continuously control moving along that pyramid within one optimization. At any time, you can move along that pyramid wherever you want. It's just hard to know how to move, but you're able to do that in one optimization. So that's another powerful feature of that method. So this is image pyramid. It's important to know that. Sometimes people use it and just write a line and you read it in the paper. So you know what it means.
In terms of like the downsampling of the image that's done, is that typically something that's done artificially, like during the computation now? Or is it a matter of just like optimizing the input resolution into your system? Is it, I guess, is it more hardware design problem or software design?
The image resolution.
Yeah, so in terms of when we're doing course registration, is that just something that's like designed for from a hardware standpoint, or is that something that most people just like downsample, let's say, during
No, the image, the hardware, the question is this a hardware problem or algorithmic problem? The hardware can give you a very high resolution image. We just, algorithmically, if we attempt to solve this problem using full resolution image, you might think you're going to get better result. Because the solver is local, your result might get worse. Because the Gauss-Newton will find a local minimum based on where you start. Whether that's a good answer or not, depends where you start. When you look for a coarse version, well, it will make it faster initially, right? Then a lot of those subtle minima will disappear. As if you have a surface with a lot of up and down, right? And if you get rid of high frequency part of the signal, you're left with a nice surface, right? So you first go to where it's deep in terms of the loss function, and then you go back to the high resolution surface to do the fine registration. So it's an algorithmic problem. If you have a global solver, you could use that. But typically global solvers are slower anyway. If you go for high resolution image, it won't be probably real time. So ongoing challenge.
Last lecture we did quant registration by using Perla and made the data continuous. And that's how we associated the continuous. Like, how do I reconcile that with this? Because we are using one-to-one correspondences to make the residual of intensity.
Right, good question. There's a question that last time we had a double sum, it was association free. How do we know how to subtract which I2 from I1, right? So the answer is that when, well, from image 1, right, you have all these points, right? You start from the first one. Again, you know the point in 3D because it's RGB camera. So you read the intensity value, and that gives you this term for I1, right? Now, when you transform it and project it, you get the coordinates on image 2. You do need probably to do rounding because indices are discrete, right? Based on the projected value, find the closest index. Or sometimes people take a neighborhood, which again makes it more complicated because now every residual becomes n residual based on how many neighbor you choose. But anyway, if you pick one coordinate that is the projection here, we round it and read that pixel value from I2. So this is also another idea that is called projective data association. In literature, this is known as projective data association. So you just need to project, and then you solve the association by reading the pixel coordinates.
Didn't you use the RGB values or data set values to create the transformation matrix? I'm kind of thinking a chicken and egg problem.
Will we use the RGB or intensity value to do what?
Didn't use the RGB values as weights to find the transformation?
We don't know the transformation. At any time, at any iteration of the optimization, given the current guess, we have to do this association. So they are not necessarily correct. But hopefully, every time we move a little closer to the correct association. Yeah, that's the problem too. That's a good point. Because whatever is the guess, this difference is not, they're not necessarily the same pixel, right? Even if there is a perfect match in image 1 and 2, right? Okay.
So is there any sense of, like, I guess, pixels and you're making those correspondences, like, it sounds like you're just matching up the closest intensity that's in the corresponding image to your current point. Is that what's happening?
The question is there any geometric constraint? Because we only use something that is called photometric loss function. What we built is called photometric loss function. So we do not perform registration in 3D. That's all we have in this formulation. Again, in the previous lecture, it is in 3D. There is a geometric relationship that can capture occlusion better. Photometric, obviously, is in the image. It suffers from occlusion. It is in 2D. Nevertheless, it is a very powerful formulation. It gives us already a lot. So we're ready to formulate the first problem. The optimal transformation is the transformation that minimizes sum of squared of these residual. And this is the least squares formulation of the problem. Why least squares? Because that's the simplest second order solver that we know, and it will give us a solution. Are we done?
Question on the last slide is really, why is the I not like the U times V times depth? This isn't P a size 3 vector? Mm-hmm. Like, it seems like we're applying I to P, but it should be like X, Y, and Z, not UV. Am I missing something here? Like, what are the actual, like, what is actually PI? Like, isn't that a XYZ coordinate?
It is. PI is XYZ.
Okay. Oh, we're finding it for each pixel. And
well, for each pixel, we have P. Okay. Right. So here we have, right, this is something one time if you go through the code or implement it, there's no other way to do it. So that's when you read the data, you see that, well, there is UI and VI, right? But it's also corresponding PI because the inverse of that projection model will give you the 3D point. However, to get that, you need the depth value, Z. The RGBD camera will give you Z. So because you know Z, you can recover X and Y in metric scale. So then you have XI, YI, ZI. So this is given, right? And then we read the pixel. So basically, when you store it in memory, you have UI, VI, that's the pixel value. Then you have XYZ for that pixel, and then you have the intensity. Depending on which one you want, you just read that from your data structure. So we have the first formulation of the problem. And I expect more from you at this point because I told you better than this. What's the problem? Say it again.
Do we need a constraint that we're minimizing against?
Do we need constraints? No, we have the loss function. Can we do better? Or is this all we can do?
I mean, I guess one problem is that you're kind of assuming that the correspondences are one-to-one, where there's probably just a small overlap between images. So.
There could be a small overlap. Even if it's big, there is a non-overlapping part, right? So that's a good point. So no matter what, when we move, there's going to be a non-overlapping part, no matter how small, between two images. And that can be easily half of the image. So as we read this intensity and evaluate the loss function, they're not supposed to match exactly. And in fact, they can be very large if at any iteration, if the transformation is not near the solution, the difference can be very large. And we're dealing with a quadratic loss function. What happens when the residual for some of the pixel is very large? They don't match. They're not basically correspond to each other. Now, I see you shake your head, but that doesn't solve the problem. What should we do? So you acknowledge that this is a problem. It's going to be a very large residual for certain right? You were almost there. Yes, M estimation. So how about we make this a robust list of squares? It's always better. It's always giving you something better than not having it, right? 99.99% of the time. So when you have it, make it robust. Usually we don't lose anything, but you do need to tune that hyperparameter. And you can do it on some sample frames. It's not very difficult. So let's do M estimation. We're going to create an M estimator. AKA robust when you add robust in your paper, increase your chance of acceptance 50%. And that's a small section when you add an M estimator. Trust me, it works. So what we have many options, but we learned about Cauchy loss function. Let's say that's the example we use. So the new problem will be should have read in here as well. We're solving, optimizing over T, and T belongs to this set or group SE3. So the robust kernel, this is the robust kernel or norm. For example, this is a Cauchy loss function. How to solve this? The previous one, we could solve it using Gauss-Newton or Levenberg-Marquardt. And we already learned that the difference that we'll make when it's on Lie group, well, we need to derive the Jacobian. You've seen some examples. We can do that. And then the integration rule will be different. We have to use exponential map to integrate the transformation. So we covered that in the optimization lecture. But this is no longer a least squares problem, because now it's wrapped around another loss function. And It's not a least squares problem. How can we solve this? While you think about it, there's a comment in chat that we can identify landmarks in 2 images. Matt is saying that, and so I'm going to take this comment as an opportunity to explain the difference between direct and indirect methods. We are not extracting landmarks or features from the image. You could extract orb features, sift features, surf features, using deep learning to extract features. That would be an indirect method. Indirect methods abstract the image into a set of features. The set of measurements, instead of more than 600,000, will be substantially smaller. Maybe you have 100 images, 100 features. But the quality of features will be higher. But you have to discard a lot of information to work with those high-quality features. Direct method consumes the raw data. We are directly using pixels. So we're using a lot of lower quality features in some sense, and these are pixel values. But we use a lot of them. All of them here. And that's called direct method. We are directly working with the camera images. So there was an era that was a lot of debate which one is good. Indirect methods are better when the transformation is large. Indirect methods are also very good for solving non-temporal registration problems. In particular, in loop closure, when we detect the same place, we see the same place from a completely different angle. It's challenging for direct methods to solve the registration problem because the initial transformation is very large. Whereas indirect methods can solve that. An example of that system is Orbislam that uses bag of binary words to extract features, detect the loop closure, and then use features and ransack to come up with a rough registration of very far frames. And then in the back end, the graph optimization will solve the SLAM problem. Direct methods are not very good at solving that problem. But when you are dealing with small movements sequentially, which is the case for temporally tracking, they tend to be very powerful. They're very robust. In direct methods, if the environment is featureless, well, the algorithm is doomed to fail. Imagine it's uniform. It's all grass. It's all snow. It's all like a planetary data set. The helicopter from NASA is flying over Mars. I saw it on the internet. There was a video, right? And the land is just so uniform that you just don't have features. Or features are very unreliable. You might detect, might not. Now, direct methods work well in that situation. As you move, you use all the pixels to track the camera image. So, and you can combine them as well. There are hybrid methods, such as SVO, to combine them. This particular method that we talk about is called DVO, direct visual odometry, or dense visual odometry. So direct methods can be also dense or semi-dense. We're talking about dense direct method here. We're using an entire image. You can also subsample, maybe extract edges or some better high gradient pixels in the image, for example. Then you can work with a semi-dense direct method. An example of direct semi-dense method is direct sparse odometry, DSO. That's an example of that. But that uses a sliding window optimization. It's not frame to frame. So that's the story of direct, indirect features, pixels, dense and semi-dense. So how to solve this? keep talking, you refresh your memory. We need an answer here. We're not going to move on.
Convert it to weighted least squares with weights depending on the residual.
Right, that's a good idea. What was the name of it? We had an algorithm for it. IRLS, yes. Together we figured it out. So convert this to weighted least squares when weights will depend on the residual. Update them every time. We had an algorithm. We called it iteratively reweighted least squares, IRLS. I'm not going to repeat it here because you're going to get bored, but you know where to look if you want to solve this using IRLS. So we can solve this problem using IRLS. Now I do give you some note for I have it from previous years, deriving the Jacobian for the sake of your mental health. I'm not going to drive it in class, but it's really just the mechanical procedures that chain rule, get the derivative of the projection model, then you have the action of the rigid body on the point, perturb it, derive the Jacobian. We did it in the optimization lecture. So the Jacobian will be product of multiple steps, right? So we leave it at that. And that's the beauty of if you have a library that gives you this solver, you can learn how to construct your problem and give it to that solver to solve it for you. And that's usually a good way to save time and speed up your progress. And in fact, you can do that. You can use something called series solver. This is a solver for nonlinear least squares problem. It does provide robust kernels. It has other solvers as well, like conjugate gradient, gradient descent, and so on. So, one question. When we formulate this problem, given that we have a lot of points, somebody calculates what's the 240 times 320. So we have a number. What's the size of the normal equation we need to solve? Is this problem larger scaled or not? It is? What's the size of the problem, the linear system that we need to solve? So suppose we evaluate we convert the problem into a weighted least squares, right? It will be R transpose some W R. Now, of course, we're solving over T. Again, the W depends on the residual and its IRLS, but For one step, it is a weighted least squares. Now, if you calculate the this is probably some matrix. Let's say we calculate the Jacobian for one residual term, right? For just 2 pixels. And that will be, what's the dimension of this? What's the mapping of the loss function? The mapping is from the rigid body transformation, twist. The parameter that we will solve, the delta, will be twist, right? We integrate it using exponential map. Twist has 6 dimensions. And the loss function, the residual in this case, is actually scalar. It could be a vector in least squares, but here it's just intensity. So the Jacobian is one by 6, right? Okay. So it's a mapping from the variable to the residual, whatever is the space of residual. Because your residual as a function of twist, right, when you perturb it, it will be linearized based on some Jacobian plus some constant, right? Something like that. 6 by 1, 1 by 6. If you linearize it, you will get this model from Taylor expansion or other techniques for deriving the Jacobian. All right, so if that's the case, this is, which is essentially a square root of this weight times partial derivative of residual times with respect to twist. So this is a 1 by 6 matrix or a row vector. If I stack all of them, that will give me the entire Jacobian for the problem. And that's A1, let's say A2, AN. N by 6. N is 240 times 320. That's a very, very long, tall Jacobian, but fortunately, the number of columns are actually not very large. So the variables that we're solving are only 6 parameters. It makes it the 6th vector. So if you construct the normal equation, it will be A transpose A you probably have We need some square root of that weight here for the residual as well. But anyway, this is now, what is it? Is it still large scale? So it's only a 6 by 6 system of equations. It's actually very easy to solve. And we don't even need to store that long matrix. We can process every pixel and then sum up this AI transpose times A. So 6 by 1 times by 1 by 6, 6 by 6. And then keep adding them. That's how it will become invertible. Otherwise, for a single pixel, it will be obviously low rank because it's 6 by 1 times by 1 by 6. So when we sum over all pixels, if you have enough pixels, it will make it invertible. That's how you know you have enough measurements. And then we can basically, you can define this to be H equals D. So we only solve a 6 by 6 system of linear equations. So it's very fast. This part, it does not take a long time at all. That's good news. That's how you can make this with low resolution image. You can make this real time. So that's how we can wrap up the IRLS solver, because now you know what's going on inside. Every time inside you update the weight, solve a 6 by 6 system of equations, update the transformation, do it again until some maximum number of iterations or convergence. Now I have one last question for you before I finish. And that's when we have other sensors. What if you want to combine other source of information, such as IMU, or maybe you have post tracking from another sensor? Maybe you get, I don't know, LiDAR odometry, or maybe you have prior over your pose. You want to add it to this problem. What can you do? Sensor fusion, not just using the RGB camera. What can you do if you have other sources of information?
Can you use an EKF?
We can use an EKF. Probably, but that's very painful. We have to. We need to track two poses in this state. And we have to derive all the filter equations correctly. It's going to become, it's possible, but it's going to be more complicated. But the problem with filtering, which is next time we want to talk about it, is that once you linearize, you can never go back in time and correct it. We're after, now that we're dealing with more sensors and more sources of information, we're after something more modular, something more flexible. We can go back in time and correct past mistakes and linearizations.
As new measurements or previous beliefs get integrated, we can add them as constraints to our optimization problem.
As we get new measurements, we can add more constraints. By constraints, you mean constraint problem or extra objective, making it multi-objective?
I think multi-objective.
Yeah, so that's a good observation. A sensor that we used was RGB camera, and as a result, we derived a residual, a measurement model, and an error definition that allowed us to solve the optimization problem. in the context of SLAM, we're going to call this a factor, right? In factor graph, this is a factor. So a factor, it will be an edge in the graph that connects two nodes, and that edge represents this residual. So everything we talked about can be one edge in that graph. So next time we want to answer this question using factor graphs or graph SLAM, okay? Then we're going to talk about different nodes and different edges, right? This is your maybe camera. The camera is getting bigger as you move forward in time. That's not what we're doing here. It's the same camera. It's called spatial relativity. You move fast, objects, length can differ. They get longer if they move away from you or they get closer to you. You will know when you see the object. So then you have, well, in that context, then you have, let's say, the first transformation, the second transformation, and the third one. The first one, maybe it is, maybe you don't know, maybe it is identity, right? Maybe some prior. Or maybe you do know. That's whatever knowledge you have, you can consider that. This will be, for example, our photometric factor. And what it is, it's the same problem that we just talked about it. So it's a building block of this graph. Now we're going to solve many of them at the same time. So we're going to assemble a giant nonlinear least squares problem and then solve it at the same time for all the variables. So that will allow us to make this modular. Now if you have another sensor, you can easily add more edges. And maybe this is your IMU. Okay? This is good. This is scalable. It is too hard probably to manipulate by keep adding objectives and deriving the equations again. This will allow us to implement a library, take data in a modular way, and potentially automate how we solve it. And this is done already, and that's why we have GTSAM library. Now, G2O can also solve that, but GTSAM probably has more sensor models and solvers. GTSAM in particular has ISAM solver. That solver allows us to solve the problem incrementally online because we don't want to solve the problem from scratch every time. We want to reuse past solutions to update the small amount that we just add to the graph. So that's also available in this library. So again, the message is that what you read as factor is this measurement model. Okay? And that's what you implement in your homework 7. So you're really working with the library to enter data. You already know the meaning behind it.
So this might be a dumb question, but do each of these nodes imply like temporal co-location? Like each
that now required? So for each of the
Edges, do the nodes have to be temporally co-located between the measurements?
No, that's a good question. The question is that now the nodes that I'm writing here, in this rough figure, I have t maybe 0, right? 1, and 2. You're asking that, can we have a node, for example, at time 12 that will get connected to this node? Absolutely, and that's loop closure. That's why this framework is so flexible. Now, the constraint between T1 and T12 obviously is not going to be IMU. We did not continuously move from T1 to T12. There's a sequence in data from IMU that we need to incorporate temporally in the graph. What we can have here is knowledge from place recognition, re-observing maybe the same features, re-observing the same place. So it's a topic on its own, but it is possible, and that's precisely why this framework allows us to solve a SLAM. We can add not only temporally correlated data, but also non-temporally correlated that allows us to remove drift. There is no way to remove drift from the trajectory without having this non-consecutive edge in the graph. That makes it a SLAM. Without this node, without this non-consecutive node, it is just an odometry. With this, it's a SLAM. So that's a very good question. And that's what we're going to talk about next time. So that's the next 2 lectures, we're going to talk about a SLAM. So we will focus on building the framework. The edges can come from typically variety of sensors. And that's why it is sensor fusion, because you can have different sources of information. So that's the end of this lecture. See some questions. So the number of terms is 76,800, not 600,000. I wish I could go back in time and fix that, and that's the problem. That's exactly what happens in filtering. The mistake was made, and we can never fix it. And that's a consequence of a causal data processing. In control, everything is causal. In the smoothing framework, it can be non-causal. When you go back in time, you can use future to correct past, and that makes it non-causal, and that's okay for perception and estimation. Okay, so we end the lecture, but I will answer questions on chat and in class if you have any. Thank you.